Okay, we'll move on then back to Bob. How do I determine the maximum permitted earth fault loop impedance values for 110-volt circuits installed to supply 110-volt socket outlets in a workshop? Bob, we're not hearing you at the moment. I think you're muted.
Didn't notice that.
That's it.
Okay. 110 volts. That's sort of typical of reduced low voltage systems. In Chapter 41 to the regulations, there is a protective measure, reduced low voltage. Now, reduced low voltage is something that is only applied in the UK. Didn't use it in Europe, so it's not mentioned in things like the IEC documents that reflect BS 7671 or the harmonised documents. So it's specific to the UK reduced low voltage, and it's commonly used as an alternative to self or PELV systems. Self is where we're dropping the voltage to commonly below 50 volts, and that makes it obviously a lot safer, protecting people against electric shock. It's defined in the wiring regulations as a system in which the nominal line-to-line voltage does not exceed 110 volts, and the nominal line-to-earth voltage doesn't exceed 63.5 volts, although 63.5 volts tends to be on a three-phase reduced low voltage system. Single-phase systems tend to be 55 volts to earth. So you can see it's inherently safer, and it's usually supplied through 110 volt centre tapped earth system with the source of the supply of the circuit provided by a double wound isolating transformer. There are British and European standards that the transformer has to comply with, and usually, for instance, the midpoint of the secondary winding on a single phase transformer would be typically connected to earth, give the 55 volts to earth. So normally your line conductors, you've got two line conductors on the output. If you measure between them, that's 110 volts. The centre point is connected to earth, so that's the line to earth, 55 volts. So things like that, every socket and coupler must be dimensionally compatible with the use to which it's being put. It shouldn't be confused with other sockets, 230 volt sockets, and usually you're identifying them by colour, i.e. yellow coloured sockets, couplers, plugs, that sort of thing. As I say, it's a little bit above the normal self or PELV systems, as I say, 55 volts rather than 50 volts. What you tend to have is protection by basic protection, so you can't touch the live conductors first of all, and also you would employ automatic disconnection of supply as you would in a normal mains supply to protect people against fault. So for fault protection, you're using ADS, so you're relying on things being connected to earth. The only difference between automatic disconnection of supply on a reduced low voltage system compared to an ordinary 230 volt system would be that you need overcurrent protection in both line conductors. As I mentioned, the output of the transformer is effectively two lines, so you would need a fuse or a circuit breaker in each of the lines. Alternatively, you could use an RCD, I suppose. So I mentioned the importance of connection to earth. So all exposed conductive parts of the reduced low voltage system must be connected to earth. And the earth fault loop impedance at every point of use, including socket outlets as mentioned in the question, must be such that disconnection during a fault occurs in less than 5 seconds. So the disconnection time for reduced low voltage systems is 5 seconds. So we don't need to worry about the 0.4 second disconnection time for other socket outlets. Where a fuse or circuit breaker is used, maximum earth fault loop impedance is determined in the normal manner, i.e. the earth fault loop impedance times the current that causes operation of the protective device should be less than the nominal voltage. The nominal voltage in this instance being 55 volts. So there are tables specific for that in the wiring regs, specifically table 41.6. We have tables for 230 volt systems for fuses and circuit breakers 41.2, 41.3 and 41.4, but specifically for reduced low voltage systems there is a table 41.6, and that gives you the maximum earth fault loop impedances for these systems. So if you've got a socket outlet in a workshop or a socket outlet in a construction site, because that's where they're commonly used, that's where you'll get the values. Now, with regard to measuring them, some of these modern multifunction test instruments will work on 110 volt systems to measure 110 volt circuits. Alternatively, if you didn't have that, you could simply measure the R1 and R2 using a continuity test instrument and add that to the input ZE, if you like, on the transformer. So there's a couple of ways of doing that. The table, by the way, just for introduction, my reg book is on page 68 of the current reg book, table 41.6. For instance, a 16 amp type B circuit breaker would, the maximum earth fault loop impedance would be 0.65, you know, as an example.
Okay. Thanks, Bob. Any questions for Bob around that? No? Okay, thank you very much.